Hi, in this video, I'm going to explain the binary numbers. So probably some of you have heard that computers, they are a bunch of switches, on and off switches, and that's pretty much true. Now, they are connected in a very intricate and complex and logical way, but at the very basic physical level, they are switches and electricity just flow through these switches. Now, when the electrical current does flow, then the switch is on, otherwise it's off, right? Just like a light switch. Now, that's what happens at a physical level, but and then we kind of map these current or the switches, whether they're on and off, to a logical values. And when a switch is on, it's a logical one. When a switch is off, then it's a logical zero. Now, these on and offs, they are further mapped in a logical level to what we call bit or binary digits, right? So you've probably heard this before also, that computer system, at least the current ones, they are really just binary systems. And that has to do with on and off switches or ones and zeros. So a bit, as we just said, it can be either zeros or ones. So obviously one bit can represent two different values, right? Okay, what about two bits together? How many different values can it represent? So you can think of it in a way that, given two bits, each of them can take a value 0 or 1, then how many different combinations can the two bits together make? Well, it turns out if you write 0, and we can take it to the next level. So what if there are 3 bits? How many different values can 3 bits represent? So pause the video, maybe think about this for a moment. So if you write out all the possible definitions, combinations, and here is a table of them, there are 8 different values that 3 bits can represent. So I hope by now that you kind of see a pattern of, that relates the number of bits to the number of different values those number of bits can represent. So can you think of a formula that actually gives that defines that relationship? And as it turns out, it is this, that if there are n number of bits, then we can represent 2 to the nth power different values using those n bits. And you can use this formula to kind of go back to the previous examples and make sure you do verify that this formula is correct. Anyway, so the next question is, okay, fine, we have a bunch of bits, then how do we use them to represent numbers? Now, before I dig into the details, I want to remind you that bits by themselves, they really have no inherent meanings, like just a bunch of zeros and ones that form some sort of pattern, right? However, we as humans can assign meanings to bit patterns. So for example, this is one bit pattern, 0101. We can assign a number, say 5 to it. Or another bit pattern, this is 11000001, right? We can say this bit pattern actually represents the letter A, and so on and so forth. Now, obviously, we cannot just assign kind of random bit pattern to random numbers or random letters, and we really need kind of a systematic and a standard approach to kind of assigning meaning to these bit patterns. And there are such standards, and we're going to start with an example that how do we use these bit patterns to represent numbers. In order to do that, though, let's review how a system that we are very familiar with, the decimal numbers, how it actually works. So the decimal numbers like 12, 793, so on and so forth. Now, each of the digits in these numbers can assume any of the 10 values, right? 0 through 9. So that's why it's called decimal. Decimal means 10, right? Dec. And now, if we think a little more carefully, numbers like 10, which is 10, and 100, which is 100. Now both of these numbers have the digit 1, right? Now, does the digit 1, do they mean the same thing in both numbers? Well, not quite, right? Because this 10, obviously it's a 10, and this 100, this is 100. So the 1 has a slightly different meaning in these two numbers. So exactly what is it? Let's look at a slightly more complex number, which is 1024. Now, the reason this 1024 actually represent 1024 is that if we break it down, the number 4 here, it means 4 ones, right? And the 2 here, it really means there are 2 tens. And 0 here means there's 0 hundredths. And 1 here means there's 1 1000th, right? And that's how we get the value of this number. Now, we can rewrite this all kind of in terms of the base 10 here by doing 1, we know it's 10 to the 0th power. 10 is 10 to the first power. 100 is 10 to the second power, and 1000 is 10 to the third power, right? And you can imagine this this kind of can go on for bigger numbers. And one more thing, kind of definition kind of thing is the digit that's on the right side. That's what we usually call the least significant digit, and then the significance of it increases as we go to the left, and the leftmost digit is what we call the most significant digit. And as we can see, each of these digits, the true value that they represent is the digit itself multiplied by the base. In this case, because we're in the decimal system, so we're using base 10, the base raised to a certain exponent. And the exponent, it starts at 0 at the least significant digits and increases by 1 every time we kind of go over, or go to the left, the digit on the left. So just to recap, in a decimal system, each of the digits can take on one of the 10 values from 0 through 9, and the base is 10, and the exponent starts at 0, and as we go to the left, or go to the most significant side, it increments by 1. Now, for the binary system, the rules are very, very similar, except obviously each of the digits can only take on 2 values, 0 or 1, and the base, therefore, is only 2 rather than 10. The rule that applies to the exponent is the same in both systems. So let's look at an actual example of a binary number. This is a fairly trivial example, just 0001. And to figure out its true value, we write it out in this form. Remember, the base is 2 instead of 10. And the exponent is, we start at 0, 1, 2, and 3. Right? And so if we work out this number, this is basically just turns out to be 1, which is kind of what you would expect. Now let's look at a slightly more interesting example, 1011. So this is again in binary. So what is it in a decimal system? So we write this out again, just same rules apply. The least significant digit is 1 multiplied by 2 raised to the 0th power. Second digit, 1 multiplied by 2 raised to the first power. Third digit, 0 multiplied by 2 raised to the second power. And the last one, 1 multiplied by 2 raised to the third power. Now, thing up 0. And again, this one is the least significant bit, and this one is the most significant bit. Now, and also sometimes we like to say, the least significant bit is bit 0. The one to its left is bit 1, and then the one left to it is bit 2 and bit 3, and so on and so forth. So we can kind of address individual bits by its kind of a bit position. Now another problem kind of is, if you look at 1011, this could, we said it's a binary number, but it could very well be a decimal number, right? And in decimal, this is 1011, right? But in binary, it's 11. So in order to distinguish binary numbers from decimal numbers, we usually prefix a binary number with 0b, right? Stand for binary. So if we write it out this way, 0b, and then zeros and ones, then it's very clear that it's a binary number. So having shown you the example how to derive the values for a binary number in decimal, I would like you to pause the video now and try to figure out the decimal value for all of these binary numbers. And assuming you've done that, well, at least most numbers here, except maybe the last one, here are my answers. And yeah, please do verify your answers, and hopefully you got everything right.